Okay, everybody. Can we please take a look at the sheet that I just gave you? So we are looking at performing transformations today. So you are going to be given a function. Maybe it's one that you recognize with a parent function. Maybe it's just some random thing. It doesn't really matter. Okay, so today, what we are going to learn about is how to take this parent function, pick it up, and move it around. So we can slide it left, right, up, down. We can flip it over. We can shrink it. We can stretch it. We can do all sorts of different things. Okay, and they all follow. Guys, if I could not have to talk over you, that would be delightful. Thank you so much. Oh. Poor vocal cords. Any hoosers. So I forgot completely what I was talking about. We can do anything to these functions, and they all sort of follow the same general pattern. So once we learn that pattern, we can do anything if we recognize what is being done, that is. Okay, so let's take a look at the first thing that we could do. So I apologize again that yours are not in color, but if you wanted to, if you have some different colored things, you could trace over them in the other colors if you wanted. So what this is showing you is here is my original function, just like we were given up at the top. So in black, there is that function as is. If I wanted to shift this function upwards, as seen here in a red color, all I have to do is add 3 to the function. So I just take whatever it is and I just tack on a +3 on the end. That will shift the entire graph up 3 units. Think about it. If you take y equals x, right? That perfectly diagonal line through the origin. If you just do y equals x +3, what happens to that whole line? Doesn't it shift up 3 units? Right, because now you'd start at +3, but then follow the same slope. So if you want to do a vertical shift, you could just add whatever amount. So naturally, if I wanted to move it down, I'm just going to subtract whatever I want. So that is probably our easiest transformation. Shifting it up, I just add, down, I just subtract. Okay, make sense? And I think you've seen some transformations before, right? You guys said Miss Pashka did a lot?
Yeah,
She did this for like 2 months.
yeah.
Oh, good. So you guys are going to be aces. Okay, now a little bit trickier. So stay with me here. If you want to shift left and right, it's not quite as easy as just tacking it onto the end. So if you look over here, what we're going to do is we are going to attach it to the x. So I'm not just going to add it to the end of the function. I'm going to go in there. Wherever the x is, I'm going to add or subtract the value. But here's the catch. It's actually going to be the opposite of what you want to do. So yes, it can absolutely be a little bit confusing, but let's see what's happening here. If I take my original function that's drawn here in black, if I wanted to shift it to the right 2 units, normally we think of moving to the right as a positive value. It is, but the formula is actually x minus h. So that's why it ends up looking like this. I don't know. But that's when you start plugging it in, you'll see all the numbers match up that way. So if I want to go to the right 2, I'm actually going to write it as a -2 inside the parentheses with the x. So whatever I'm doing to that x variable, I'm going to subtract 2 if I want to go to the right 2. So naturally, if I want to go to the left the other way, I'm actually plugging in. Well, again, so if the formula is f of x minus h, if you plug in a -4 for h, negative minus 4, right? Negative and a negative turns into a positive. So the end result is that it looks like this. So if it's in there with an X, that's your cue. Okay, I'm gonna do the opposite of what it says. I know it says a +4 there, but that really means go to the left 4 units. When I see a -2, that really means go to the right 2 units. A little tricky, but you'll get the hang of it, or you already have the hang of it because you're a Mrs. Bashka graduate. I don't know. Okay, so again, over here, we sort of spell this out for you. If you see a plus, you're going to go to the left that many units. If you see a minus, you're going to go to the right that many units. Okay, so far we're all right? All right, let us flip. Now, what should I do if I want to flip the whole thing over? If I want to flip it over the x-axis, think about what has changed. Here, let's just take this particular point right there. It's still, so its coordinate was 2, 1. Now, if I flip it over, it's at 2, -1. So my x has not changed, but my y value is now, instead of being a +1, now it's a -1. That's interesting. So let's take maybe this point over here. Oh, wait, that's not on the, here's the original. So that was at 2, -4. When it flips over, look, I'm sorry, -2, -4. When it flips over, now it's at -2, +4. So what am I doing? I'm taking all of the y values and I'm multiplying them by -1, basically. So now I'm putting all the y values, I'm switching all of their signs. So how do we accomplish that with a function? I'm just going to multiply. Remember, f of x is really just y. So if I just multiply all the y values by a negative, that's going to get me that reflection over the x-axis. That's all I'm not moving it left or right or anything. I'm not doing anything with the x's. It's the y's I'm flipping. So far, so good? Okay. Now, if I want to go the other way, let's say I do want to reflect it over the y-axis. So let's take a look what this would look like. So again, my original is here in black. So if I want to now flip it over the y-axis, now I can kind of play the same game. So this point right here at 2, 1 now flips to here. Look at how it's now the x's that have changed. So now I want to go to -2, +1. This one, oh wait, this was my original. So at -2, -4, now we're at +2, -4. So all of my x's have changed signs. So how do I accomplish that in the function? I'm just going to take all of my x values. So notice I'm inside here with the x in the parentheses, and I'm going to multiply all of them by a -1. That's going to achieve the flip over the y-axis. So far, so good? I'll take that as a yes. Okay, now let's talk about making it taller, stretching it up, or squashing it down. So here's this one. So look at what we have done to the original function here in the middle. I can, let's start with the blue one. So the blue has now, it's gone from here, right? And now it's here. We have stretched this one up tall. Let's follow the points, okay? So if I take a point, like, let's just stick with our same 2, 1. Now I'm at 2, 2. Oh, that's interesting. So the x hasn't changed at all, but the y certainly has. Let's follow another point. Here's 3, 3. Now I'm at 3, 6. So apparently what's happening with all of my y values, let's see, this one was at -4. Now we're at -5, -6, -7, -8. I went from -4 to -8. What's happening to all of the y values? They're being multiplied by how did I get from 1 to 2 and from 3 to 6 and from -4 to -8? I'm multiplying by 2. So, oh, there it is. If you, I mean, it's right here, right? So it's showing me, hey, you're going to do 2 times all of the y values. And that stretches your function taller, makes it 2 times as tall as it was before. Everything gets stretched long. What if you want to squash it? Now, we're just going to multiply by some fraction, right? Something less than 1. That would squish my function down smaller. So you can take a look. It might be a little hard to see, but this one here is the red one. Let's see if I, it's hard to even see on the screen the difference between the black and the red. Let me, there it is. I know I had a red marker. This is the red one, if you can't see it. And I know you don't have any color on your sheet. Okay, so there's the red one. So if I see what's going on here, so let's take a point from the original, the black function, see what's happening to get to the red. So I had x was at -2, -4. Now I'm at -2, -2. So the x's didn't change, but my y sure did. I went from -4 to -2. Interesting. Let's pick another point. How about this one right here? This was at 3, 3. Now it's at 3, 1.5. How am I going from 3 to 1.5? Well, this one goes from 1 to 1/2. This one went from -4 to -2. I'm multiplying by 1/2. Do you see that? And that has now compressed this function. All the y values are now half of what they were before. And that results in a squashed graph. Yeah? Easy peasy? All right, all right. Let's see what else we got on here. Okay. Whenever we do things with the x, things get complicated. I guess, yeah, okay, never mind. So let's look at what's happening here. I'm like an accordion. I'm going to stretch it out horizontally, or I'm going to squash it together horizontally now, right? So now I'm looking at what happens with my x's. So I have my original function still, this one here in black. Let's do, let's go to the blue. Let's see what has happened here. Now, I know you might be thinking, oh, yeah, just take half, right? Because this was at 3. Now it goes, look at my x values. Went from 3 to 1/2. This one here was at, what's that, 5? And I went down to 2.5. So I know you're thinking in your head, oh, yeah, okay, we'll just divide all the x's by 1/2. But remember, with x's, everything is like opposite land. So what's the opposite of, I'm sorry, I said dividing by 1/2. That's not what I meant. I meant multiplying by 1/2. I'm taking half of all of these x values. What's the same thing, or what's the opposite of multiplying by 1/2? Instead of multiplying by 1/2, that's the same thing. I'm on the opposite.
Oh,
Jake? I want to, yeah, instead of multiplying by 1/2, the opposite thing to do,
multiply by 2.
multiply by 2. That's what I want, yes. So just like, remember when we shifted it left to right, we were like, okay, if I really want to go to the right 2, I actually have to write it as a -4 because it's the opposite. So I really do want to multiply by 1/2, but I can't do that. I got to do the opposite. So instead of multiplying by 1/2, I times by 2. Weird. I know. It is weird. So if you take a look, this sort of summarizes it. If you do some value times x, you are going to divide all x values by b. Divide them by b. So if I put a, let's just say I had f of 3x. What this essentially does is it takes all of my x values and divides them by 3. It's going to shrink them back to 1/3 their size. So it's actually going to, I know you think, okay, timesing by 3, it should get bigger. No, it does the opposite. It compresses everything by 1/3. It's going to do the opposite of what you see. It's not going to times by 3. It's going to divide by 3. You with me? So all of the x values that were out here now get shrunk in. If I have a fraction there, right? So in this case, let's look at the red one. It's 1/2 times x. So what's that really gonna do? That's gonna multiply everything by 2. So this actually stretches it out. I'm gonna take all of my X values. Let's see one that we can find right here. So here it was in black. It was at 2, 1. Look where it ends up. 4, 1. So I have essentially taken my X coordinate and times it by 2, even though that's what's in there. You always got to think, okay, it's the opposite of what it's telling me to do there. I'm not going to, that doesn't shrink it by 1/2, it times it by 2. Confusing, I get it, I totally get it. The only way you're gonna get good at this is by practice. Good thing we'll do plenty. Okay, one left. What in the world? This looks like a weird, I don't know, insect of some sort. What's happening here? Well, take a look at what we have. We have the line y equals x. That nice, perfect green one. Oh, you can't see that it's in green, but this is in green on my sheet. So this diagonal line, that's just the line y equals x. If you reflect a graph over that line, you get something called the inverse. Okay, and this is how we denote it, f, and it looks like to the -1 power, but it's not. That's just notation for inverse. We'll be dealing with inverses quite a bit in the next chapter. I think it's the next chapter anyway. So if I take that line y equals x and I reflect my function over that line, you get something called the inverse. How do you get it? Well, since x and y are equal to each other, you can literally just swap them with each other. Right? So I'm changing it over the line y equals x, so I just flip them. So let's see if we can follow. So this point here would correspond with this point here. Look at this point's ordered pair. That's at, what is that, 5, 0? And that corresponds with this one here. And look, literally the x's and y's have just swapped. That's 0, 5. Huh, look at this one. This one is at 2, 1. Where is it over here? 1, 2. The x's, oh, sorry, you guys can't see. You gotta tell me. So, yes, that's how you achieve the inverse function. More on that to come, don't you worry. Any questions right now? A lot to take in, but it sounds like you guys have seen a lot of this before. Yes? Some of you say so. Has anyone never done a transformation before? I guess I should ask that. You've never like shifted the graph even left to right, up and down? Everybody has at least done that? Okay, cool. So let's see what I've got for us now. Is this the one I want? It is. Okay, so let's try this one together. Or at least I'll start you off. Anybody have any plans after school? I have to go to. What's this? For football stuff? When did you see- oh, probably Thanksgiving. You go back. Oh,
Same here.
yes.
Is this not the home party?
No.
Can you work out with the partner?
Well, let me get you started. Hopefully, it's just Canadian. Sorry. Okay, so if you take a look at this sheet here, you get to pick, but we're all gonna pick the same one together, at least on the front. Maybe on the back, I'll let you do what you want. But on the front, see in the very first box, it says you pick the parent function and perform the translations below. So my question is, we could do one of the parent functions that we learned yesterday, like a y equals x squared or a something, or we can make one up like on the sheet that we just had. So we could make up a design like this. What would you rather? One of the ones from yesterday? I'm hearing?
Makes you like y equals x.
No, that was too easy. Let's do, well, let's start out with y equals x squared. That one's not bad. Yes.
I think we
So-
should do
Y equals
absolute value of x.
Yeah, absolute value.
Yeah, absolute
No.
value. We all say absolute value.
I don't, that's fine. I don't care.
I would ask you that.
Absolute value of x. Okay, so everybody go ahead and in that first box, draw the parent function y equals the absolute value of x. Hopefully you already know how to do it. Okay, so who can tell me in number 2 here, I'm supposed to take this function and add 3 to it. So what is this gonna do to my graph? Yes, the whole thing just gets shifted up 3 units. So I literally take my graph exactly as it is. And if I could imagine just picking it up and shifting it up 3, that's what I'm gonna do. So my vertex there now starts up at +3 and then goes up. And here is a great way. I know these, these first couple ones are easy, but I want you to get in the habit of checking this. So this is really y equals absolute value of x plus 3, right? So if you plug in a number, like, look at my graph. When I plug in 1, I'm expecting to get out 4. If I plug in 1, do I get out 4? Yes, if I plug in -1, I should get out 4. I still do. So I'm begging you to check a point or two at least to just see, okay, did I do the right thing? Because how easy, especially with the X's, did you go the wrong way? Did you go the right way? Did you flip the right way? So please get in the habit of just checking 1 or 2 points. So now for number 3, what we're really graphing is not y equals absolute value of x anymore, but now it's the absolute value of x plus 2. We have that plus 2 in there with the x. So what did we learn from the notes? Where am I moving this graph, Braylon?
To the left.
To the left. Just like my twin says, everything you own in a box to the left. To the left. Let's check a point. And now you can see how it works out with those x's being opposite. So for example, when I plug in -1, I should get out +1. Let's see if I do. If I plug in -1, -1 plus 2 is 1, absolute value 1 is 1. So yeah, when I plugged in a -1, I got out a +2. I mean, sorry, +1, just like I was expecting. Throw in one more point if you want. If I plug in -4, according to my graph, I should get out a +2. See if you do. I do. So I know that I've done it the right way. I didn't accidentally shift right when I should have gone left or whatever. Get in the habit of checking, okay? Now, can anybody tell me what in the world multiplying the whole thing by 3 is, what will that do to my graph? Jake.
Stretch it.
Right, it's gonna take all those y values and stretch them. So I'm going to end up with a more narrow graph.
With the, just make the slope becomes 3 instead of 1.
Yes. So. I'm going to take all of my y values and I will now times them by 3. So also sometimes it helps if you want to draw the parent function and then draw the new one, like if you have a different color or something. I don't care. sometimes that can be very helpful. So I'm gonna take all the y values and instead of being at 1, now you're at 3. Instead of being 2, now you're at 6. These are gonna come like this. And same thing here. Bloop. Okay, so far so good? If you want to check a point, not a bad idea. So now remember, this is 3 times the function. So I'm going to do 3 times y equals x. Oh, absolute value of x. Oh no, this we're sort of not working out too well. So let's see, according to my graph, let's just plug in when x is 1, y should be 3. If I plug in, oh wait. If I plug in 1 for x, why do I have this backwards? Oh, because I don't want to put it over there. I want y equals 3 times my function. Oh my gosh, silly goose. So when I plug in 1, I should get out a positive 3, and I do. Okay. There we go. That's much better. When I plug in a negative 1, I should still get out a positive 3, and I do. What's going to happen in number 5? Jake.
It's gonna make it a negative graph. It's gonna go in opposite direction, so the vertex will be starting at 0, 0,
Exactly. If you are going to multiply your entire function by something that's negative, the whole thing's going to flip upside down. And furthermore, I'm not just multiplying by a -1, I'm multiplying by a -2. So not only will it flip over, what else is going to happen? Jake, tell me.
It's gonna stretch it out.
Yeah, so here's one, I'm gonna draw the parent function again, just because I think it's a little bit easier to see. So there's my parent function. And what I need to do is I need to multiply all of the y values by -2. Right? So 0 times -2 still stays there. So let me switch colors. But now, instead of being at 1, 1, I'm gonna do 1 times -2. And I'll be at 1, -2. Same thing over here, right? Because 1 times -2 is still -2 there. Take this one. That was at 2, 2. So let's take the y value, ladies. Let's take the y value and times it by -2. So I was at +2. Now I'm going to be at, instead of being at +2, where am I? -4, Henry. Thank you. So I get 1 there, and the same thing's happening over here. So this would be my final graph. How about that? So again, I'm going to take the entire function, oops, and I'm multiplying it by a -2. So I'll have -2 times the absolute value of x. So let's just pick a point and make sure that it works. How about this one right here? When I plug in 1 for x, I should be getting out a -2. And I do. Try it this way. Let's pick this one. If I plug in -2 for x, I should get out a -4. I do. So I know I've done that one correctly. Okay, now we're getting into the weird stuff. That's happening with the x. So this is what the function looks like. Y equals absolute value of 2x. It's inside there with the x. I'm going to draw the parent function because I think it's helpful. You don't have to have it, but I think it's very useful to see it on there. What did I do with these again? What is, just tell me what's going to happen.
Divide the x
Yes. So I know you think 2 times something, it should get bigger. It's the opposite with x's. It's actually going to shrink. All the x values are going to get divided by 2. So every x value that I have an x value of 1, now it's going to be a half. I had an x value of 2, now it's 1. I had an x value of 3, now it's 1 1/2. Same thing over here. These are all going to shrink in. Bloop. Bloop. Particularly for these, I beg you to check a few points. The x's can be very confusing. So let's see, this one on my final graph, when I plug in 1, I should be getting out 2 for y. If I plug in 1, does 2 come out for y? It does. Go the other way. If I plug in -1, do I get out positive 2? I do. So there is me like an accordion squishing all these values in. So far, so good? Okay. This one, you are supposed to do 2 things? You have to do 2. What are the 2 transformations I'm doing here? Evan?
Down 6 over to the left 2.
Exactly. Now, let me ask you this question. Does it matter which order you do this in? What do you guys think? Does it matter? If you go, it doesn't matter. For your translations, you can do them in any order you want, as long as you do all of them. Okay, so if you can do them all at once, that's fine. If you want to take your time and do one at a time, that's okay too. You do whatever you got to do. So there's my parent. I'm going to take each point and I'm going left 2, down 6. Okay, since this one's not too bad to do at the same time. So I'll take I always start with the vertex. Left 2, down 6. And then I know I would just follow my slope up 1 over 1 from there because my slopes didn't change at all. Those branches are still going to have the slope of +1 and -1. So that's fine. So if I were able to pick that V up and just move it left 2, down 6, there would be. So let's pick a point here. So what would this function look like? It would be y equals absolute value of x plus 2 in there and then a -6 on the end. So let's just see. When I plug in 0, looks like I should get out a -4. Do you? Yes, you do. So if you had shifted the wrong way, it's always good to check 2 points also. Because if you had shifted right instead of left, you actually still would have had a value there. So it's never a bad idea to check a second point. So this one, for example, is at what? -4, -4. So if I plug in -4, do I get out -4? I do. So if you want to be super sure, plug in 2 points. And number 8, what do we have here? Whew. What is this going to do to everything? Let's go piece by piece. What does a -4 in there with the x do? Shifts it which way? Henry, what do you say?
Right.
To the right 4. Okay, so I'm going to have a shift of right 4. And then what does this times by a -1/2 do on the outside? -1/2 times the whole thing.
It's going to have it point down. And it's going to press and shrink.
Yeah. So this, I'm doing this to the y's. So multiply by negatives, now I'm going to flip it upside down. And now all my y values are going to get multiplied by a 1/2. So in essence, I'm going to like shrink this graph vertically. Going to squash it a bit. Okay, so that chunk tells me to do y values times -1/2. So again, it doesn't matter in which order you do these two. I would probably do this one first, just so we can kind of stay on the origin. It's a little bit easier, and then I'll just move it to the right for. So I start with my parent function. And now let me do this. I'm going to do all the y values times a -1/2. Okay, so 0 stays at 0, but now instead of y being a +1, +1 times a -1/2 is now -1/2. +2 times -1 is now, or -1/2, sorry, is now at -1. Oh, why am I doing this? Oh, because this isn't my final graph. I was at +3, now I'm going to be where? Evan? Correct. -1.5. Same thing happening on this side. So that's at a half, -1, -1.5. So there's that first part. There's the times by -1/2. Now I still need to pick this up and move it to the right 4. But I think it's a little bit easier to do that than to do the 4 and then do the times by -1/2. It just gets a little crazy. So that vertex is now going to go 1, 2, 3, 4. And then I know that's at a half, be at a -1, and so on. That would be my final. So let's see, let's take this point. It seems to hit right there nicely. So what this graph would, or my function would look like, -1/2 times the absolute value of x minus 4. Let us see what comes out. If I plug in 0, I'm expecting to get out -2. 0 minus 4 is -4. Absolute value is 4 times a -1/2. What do you know? It's a -2. Another beautiful day in Algebra 3. Any questions? Okay, let's talk about what I want to do on the back. So you're going to pick the function here. What I'm just going to say what you can't have. So you are not allowed y equals x. If you make all the other ones are fine. I mean, I don't know why you'd pick some of the more complicated ones, but you can. I mean, you can do whichever one you want. If you make your own, I'm going to say that it has to, I mean, you would need something similar to this. You can't just pick like a straight line. So I'll say it needs to have let's say it has to have at least like 3 points where something changes. So if you draw your own, must have 3 pieces, I'll call it. So like that, or something. Or more, you can have more than that. Must have 3+ pieces. I mean, you can, but you want to draw all those lines, it'll take you forever.
Can we do?
You can do a y
Can we do
equals,
like y equals 1?
no, oh, you can't have a constant. I mean, the next easiest one, in my opinion, would be y equals x squared. That's not bad. You could do any of them. Or make up your own. I think that'd be fun. But you do you. No, you can't do an absolute value. We just did
Wait, that
that.
was such a dumb question.
So I'm gonna add that. Or absolute value. I think these are different transformations, but I still don't want you to just use the same one. Okay, so everybody's homework might look a little different tonight. I guess this is your homework. I guess. It wasn't supposed to be, but. That's fine. Okay, let me stop this.